Yes, hi guys. So today I am continuing with the matrices. Okay, types of matrices. I mean, first in the first lecture series, I have taken some matrices, type of matrices, definition, etc., and application as well. I discussed about. Okay, but today I am taking further some remaining types of matrices. Okay, some matrices are remain still to define, to explain that what are these matrices. After that, I'll take what is adjoint of a matrix and inverse of a matrix. That is a complete one lecture series devoted to that, adjoint of a matrix and inverse of a matrix. That is very important for management students, for engineering students, as well as for all kinds of students who are studying matrices, okay, or matrix algebra. In matrix algebra, I defined in the first lecture series what is the definition of matrix algebra, or what is a matrix. Okay, what is a matrix defined as? Okay, a rectangular array of representation of numbers. Okay, when mn numbers, where m by n, or where m and n numbers may be distinct numbers, or maybe some of them are similar numbers. Okay, so mn numbers are represented in the form of a rectangular array in m rows and n columns. This form is known as matrix representation. Okay, or a matrix. Matrix is a representation of numbers in a rectangular array form in m rows and n columns. Okay, so this is where m and n are the number of rows and columns, and this is written as I defined in the previous lecture series. So this is matrices. Now, who discovered these? I mean, matrices. Matrices were discovered by, let me introduce the mathematician. Matrices were discovered by Cayley, C-A-L by sorry, Cayley, C-A by L-A-E, C-A by L-A-E, Cayley, or C-A by L-E by, this is L-E by, I'm sorry, Cayley. So it is Cayley, C-A by L-E by Cayley, a French by Cayley, a French mathematician. He was a French mathematician. A French mathematician. A French mathematician in 1860. Try to understand. So Cayley discovered this matrices, how the matrices are, how the matrix representation of numbers is there. Okay, so he gave the definition and basic all these things. So he introduced these things. Okay, he discovered these things. Matrices, form of matrices, form of representation of numbers in the form of matrices, in the form matrices. Okay, or rectangular array of representation of numbers. But first discovered by French mathematician Cayley, name was Cayley, C-A-Y-L-E-Y, in 1860. This is a brief introduction. Still not taking the information, I mean biodata of this person. Okay, I mean mathematician, a great mathematician, one of the great mathematicians I always talk about. I'll talk about this person, I mean this mathematician, later in discussion, but not at the moment. Okay, now let me take the types of matrices further. So further types of matrices are to define, and in the previous lecture series, in the first lecture series, I discussed about what is a role of matrices in the daily life or in the management life. Okay, for the managers, the importance of this is what? Okay, what is the role of matrices in the business decision making process? Okay, so this is in today's world, it's a compact form of, okay, management decision making process, or quantitative analysis of management decision making process. Okay, so it is a systematic representation of numbers in the form of equations, and those linear equations can be easily solved with the help of matrices or matrix algebra. Matrix algebra has a very good or important role in case of managerial decision making process. Okay, so this is quantitative analysis of management decision making process. So this is a branch of this, I mean a part of management decision making process. This I discussed in the previous lecture series. Then I talked about what is the role of, what is the importance of this in higher mathematics studies. So in higher mathematics studies, matrices play an important role. because it is important in case of astronomy, in astrophysics, okay, in aerodynamics, in mechanics, okay, and as well as in differential equations, okay, and algebraic, in algebra also. So all these branches of mathematics are full of matrices discussion. So matrices, determinants, these two topics are very important for discussion. So I'll take determinant later. Some brief introduction of determinant will come here also that I'll talk about, but I'll take that in detail in determinants series. Okay, so determinant is a part of matrices also. Matrix and determinant both are complementary to each other, because with the help of matrices only we determine or we find the value of a matrix, that is a determinant. That I'll discuss in the later series. Okay, now come to the point. So what are the types of matrices? Further I'm taking 13 or 14 are discussed in the first lecture series, 13 I think. Okay, so 13 or 14 I discussed in the previous lecture series. Now I'm taking these were 20, sorry, rectangle matrices and conjugate 19, about 19. So 19 or 14, 32 or 33, they have become now 33. So 32 and 33 types of matrices are there. That I have discussed. I'm going to discuss now the remaining one. Let me take the first one. What is transpose of a matrix? Okay, to obtain a transpose of a matrix, let me take the first one. Transpose of a matrix. What is transpose of a matrix? Let me discuss about it. So a matrix obtained by transforming or interchanging rows into corresponding columns of a matrix, okay, is known as transpose of a matrix. So a matrix obtained by transforming or interchanging rows into columns, corresponding columns of a matrix is known as transpose of a matrix. So transpose of a matrix, it is or a matrix obtained by, let me take a matrix obtained by interchanging the rows into corresponding columns of a matrix. Let me take that matrix A. Matrix A, B, C, whatever. Capital letters are used to represent a matrix, but elements of it are represented by smaller letters of English alphabet. Okay, so small letters are used to represent the elements, and capital letters are used to represent the matrix itself. So a matrix, okay, a matrix A, let me take. So here, A matrix, suppose, is a matrix of order, any order. Let me take 2, 3, 4. This is 5, 6, and 3. Okay, this is a matrix A. Now, what is transpose of this matrix? So, transpose of this matrix A. So, transpose of a matrix A. Let me write here. Matrix A is represented symbolically, is represented as either A transpose or A dash. I will write. I'll take only A dash. A dash represents as a transpose of matrix. Therefore, A dash in this case is equal to. Now this row will become first column, 2, 3, 4. The rows are converted into columns, corresponding columns of this matrix. So this is 2, 3, 4, the first column, and 5, 6, and 3, the second column. Now this is the transpose of matrix A. So a matrix obtained by interchanging or transforming rows into columns, corresponding columns of that matrix is known as transpose of a matrix. So this is the transpose of this matrix. If I transpose this, so that means what are the properties of this? There are some properties of this. The property is of transpose of a matrix. Transpose of a matrix. Transpose of a matrix. First is that if I take A transpose whole transpose is equal to A only, the matrix itself. This is the first quality I mean. Then if there is a multiplication of two matrices, A, B whole transpose is given, then it is B transpose into A transpose. That means B will come before in multiplication, in case of multiplication. This is what we get in case of multiplication. These are the two properties. There are any other I'll just discuss about. And if there is a transpose of addition, A plus B. This is the third one I'm taking. A plus B whole transpose equal to A transpose plus B transpose. Doesn't matter. Okay, so this is the three properties I've taken. Okay. Now next let me take next one. What are the other types of matrices? Let me take them. This is transpose of a matrix. Any matrix, maybe a square matrix, maybe non-square matrix. Square matrix means when number of rows and columns are equal. Any matrix of any kind, I mean rectangular matrix or a square matrix, doesn't matter. So transpose of matrix is obtained by interchanging the rows into column or columns into row, whatever you say. Either change the rows into columns or columns into rows. The transpose of a matrix will be obtained. Now second, let me take second type. The second type here, symmetric matrix. Second is now symmetric matrix. Now symmetric matrix. A square matrix, let me write a definition first. A square matrix. Okay. A square matrix when it is transposed, when it's transposed gives the matrix itself. The matrix itself. Transpose gives the matrix itself. A transpose equal to A. If that means then that matrix is a symmetric matrix. So a square matrix when its transpose gives the matrix itself, then that matrix is a symmetric matrix. Is a symmetric matrix. Okay, so if I transpose a matrix and it gives the matrix itself, that means that matrix is known as symmetric matrix itself. Okay. Now let me take one instance here. So if I take a matrix here, the symmetric matrix, if I transpose that, okay, transpose of a matrix gives us the matrix itself. That means that matrix is known as symmetric matrix here. Okay. The symmetric matrix, if Aij equal to Aj or A transpose equal to A, right? Aj, or let me take, if I represent this Aij is equal to Aj transpose of this matrix. If I transpose this matrix and this gives us Aij only, transpose of any matrix, it gives us the matrix itself. That means that is known as symmetric matrix. Let me take some illustrative examples here. So if I take A is equal to, let me take symbolically Hg, and this is F here, and here it is minus H minus G. I'm sorry, this is only Hg, not minus, and this is F here only. So A, B, C are taken here, HGF and HGF. Now if I interchange this, if I get the transpose, therefore A transpose will give us, if I change this rows into columns, then I'll get A, H, G. We can take, ABC, this diagonal elements are same. ABC, three different elements we have taken. It is A, H, G. Then second row becomes second column, so H, B, F, G, F, C. Now this is G, F, and C. So same matrix is option. A equal to A, H, G. We have taken H, B, F here, G, F, C. Now if I find A transpose, okay, if I transpose means converting rows into columns or interchanging rows into columns. This first row becomes first column A, H, G, A, H, G, B, H, F, H, B, F, H, B, F, G, F, C, G, F. Now we see the same thing is there, A, H, G, and this is A, B, C here, okay, H, G, F, H, G, F. Same thing we have obtained. It means now this matrix A is the symmetric matrix. Hence, therefore A is equal to A transpose equal to D. Here we see, or this implies that A transpose equal to A. This is equal to A here. Hence, A is a symmetric matrix here. This is how we define it, the symmetric matrix. Now, the third one. What is that skew symmetric matrix? Whenever a skew word comes, we put the negative sign before that matrix. In this case, it's skew matrix. If it's there, then it will give us a negative of that matrix. That if it is a skew symmetric matrix, that means next third one is skew symmetric matrix. Third one is skew symmetric matrix. Here also it was a square matrix. Symmetric matrix we are taking, so it was a square matrix. Now skew symmetric matrix. Okay, skew symmetric matrix. Sorry, it was a now skew symmetric matrix we have to take. Skew symmetric matrix. So a square matrix again. A square matrix A square matrix A square matrix A is such that its transpose gives the negative. A square matrix A is such that its transpose gives the negative of A. Negative of A. That is, if A transpose equal to minus A transpose equal to minus A if we have obtained. That means this matrix is known as an skew symmetric matrix. Then A is a skew symmetric matrix. Is a skew symmetric matrix. Let me take an illustration. Here, if I take A is equal to, okay, let me take here 0, 0, B. Okay, and here it is minus H, minus G, minus F, and this is H, G, and F. If I've taken here, so what do we see? So we see here, now this is 0, 0. In this case, we have taken the main diagonal elements or principal diagonal elements as 0, 0. If I take 0, 0, and if I find A transpose of this, therefore let A is equal to this, then transpose of it. So this is a square matrix 3 by 3 or 3 by 3 means square matrix. So let A be a square matrix, this, then transpose of it will give us A transpose is equal to, let me write here, the first row will become the first column, that means 0 minus H minus G. Again, this is H positive 0 and minus F. This is G, F and 0. Now if I take minus sign common, if I take minus sign common here from each element, what do we find here? We have to multiply by minus sign to all. It will be 0 by minus 0 doesn't change the 0. 0 has no mean, minus 0 has no mean. It is only 0. But it will be minus H. It is minus G. We multiply minus, but we are multiplying by minus sign and taking minus sign outside. No change. This is minus sign. We have to multiply each element of this matrix here. So we know that scalar multiplication of a matrix is that we have to multiply by a scalar number all the elements of the matrix itself. This is known as scalar multiplication of a matrix. Scalar multiplication of matrix means we have to multiply each element of that matrix by that scalar quantity. So here minus sign is multiplied to each element of the. So this is positive now. So minus H into minus sign. This is positive H. This is 0 here. This is minus F here. And this is minus H here. This is minus sign. Right like this. Okay, and then this is plus G plus F. So negative become positive, and which are positive they will become negative. This is 0 here. What do we see? Is the same A. This is 0 minus H minus G, 0 minus H minus G. So the H 0 minus F, H 0 minus F. Here it is G, F and 0. G, F and 0. This is minus A. What we see here? The minus of negative of that matrix is obtained. That means if we find a transpose of a matrix, and if that transpose of that matrix gives us the negative of that matrix, that means this is a symmetric matrix. So a square matrix it is. A must be a square matrix in this case. So this is symmetric matrix. Now let me talk about the fourth one. Now in fourth one, what is the fourth type? The fourth type is, I think, unitary matrix. Yeah, unitary matrix. Now the fourth one is unitary matrix. What is a unitary matrix? Let me just talk about that. Unitary matrix. This is the fourth one. Unitary matrix. Okay. A matrix is a unitary matrix. Is a unitary matrix. Is a unitary matrix if the conjugate transpose, conjugate transpose of a matrix, and the matrix itself gives us multiplication. If multiplication of the conjugate, this is conjugate transpose. Okay, if multiplication of the conjugate transpose of the matrix and the matrix itself gives the identity matrix. That is A theta here into A is gives us I. I is identity matrix, or unit matrix. This unit matrix is obtained after multiplying by a theta into a, where a theta is the conjugate transpose. Is the conjugate transpose of the matrix. A theta is, let me write here, what is a theta? A theta is the conjugate transpose. Conjugate transpose is, first if I find out A transpose, transpose, if I take this conjugate later, but first is transpose, A transpose whole conjugate. This is A theta matrix. Okay, so if I find A transpose of the matrix and then conjugate of this conjugate complex, I've just defined what is conjugate of a matrix. Okay, conjugate of a matrix, I think there is conjugate of matrix. This is matrix A theta, conjugate matrix here. Here it is 19th one, conjugate matrix. So what is conjugate matrix? This I've taken first, no problem. So conjugate matrix is, if we find by interchanging the finding the conjugate of a matrix, or converting the conjugate of a matrix given, or a matrix obtained by changing the changing the elements of the given matrix by its conjugate complex, by its conjugate numbers. Okay, so that is known as conjugate matrix. What is that? Let me define it. So A theta is A transpose of conjugate of A transpose. This is conjugate transpose of the matrix. Means first transpose and conjugate, or vice versa. Doesn't matter. So this is conjugate here. So what is conjugate? 19th one is, what is conjugate? Conjugate of a matrix. This is the 19th one. Let me define here. Conjugate of matrix, suppose A is a matrix. If I have taken B, let me take. B is a matrix. Here it is 1, 2 plus iota, and is 3 and 1 minus iota. Okay, this is the matrix B. Then B transpose, and for B conjugate of B, we write it by putting bar sign upon B. So conjugate of B, we write here conjugate of B is equal to B bar is equal to, what we do? We just change the complex number, or find the conjugate complex of this number. 1 is 1 because it is numerical value, it is complex number. Okay, so this is 2 plus iota, it will be now 2 minus iota. And this is 3 numerical value, so same as the real number. This is complex number, non-real number I mean. So non-real number will become 1 plus iota now. Because negative becomes positive iota, plus I will become negative here, minus I will become positive I, plus I. This is how a conjugate of a matrix is obtained, by changing the complex numbers by its complex conjugate, by its conjugate number, conjugate elements is obtained. A matrix obtained by changing the complex numbers, finding the conjugate of that elements. Okay, conjugate of those numbers. So putting the conjugate of the given matrix, that matrix obtained is known as conjugate matrix of that given matrix. So here B by this matrix having complex numbers also. If no complex numbers are given, then conjugate has no meaning. Only real numbers are given, then conjugate is the same element, same matrix. But in this case, the conjugate matrix is like this. Okay. Now we have to transpose it. Transposing, making a row into columns, or columns into rows. Okay, making our rows into column, then that will give us transpose of this matrix. So this is transpose of a matrix. Now let me prove this value. If A theta into A, or multiplication will also be applied here. So I have to talk about multiplication also. This is conjugate of a number. Now what is the multiplication? Let me talk about. Then I'll prove this. Okay, so multiplication, because here A theta into A conjugate transpose of A is A theta. A theta is conjugate transpose, and A is the matrix itself. If I take, what is multiplication? I'll just define. Let me take first instance. Here it is 1 plus iota. This is 1 here upon 2. And if I take minus 1 plus iota upon 2, this is 1 plus iota upon 2. Here it is 1 minus iota upon 2. I've taken this matrix here, A. Now if I find out A theta of this, A transpose, I mean a conjugate transpose of this, A theta means conjugate transpose of this. So first find transpose of this. So here A transpose equal to, first let me find out transpose of this. First is transpose. Transpose of A will be changing the row into columns. This row will become column with 1 plus iota upon 2. This is minus 1 plus iota upon 2. And this is 1 plus iota upon 2. And 1 minus iota upon 2. And here iota means we know that from complex numbers, iota square is equal to minus 1. Here iota square is minus 1, or iota is equal to under root of square root of minus 1. This is value of iota here. Iota is used in case of complex numbers that we know about. Okay, so this is here iota mean. So this is 1 plus iota upon 2, 1 plus iota upon 2. This after changing, this is transpose matrix. Now we have to find out conjugate of this. Then A transpose whole conjugate is equal to, so it is represented by A theta here. What is that conjugate? Just changing the plus iota by minus iota, minus iota by plus iota. It is 1 minus iota upon 2, and this is 1 minus iota upon 2. This is minus 1. Here it is minus plus 1 minus plus 1 plus 1, and this is minus 1 here, and minus iota upon 2. Here it is 1 plus iota upon 2. Now this is A theta here. A theta means conjugate transpose of a matrix. This is a conjugate transpose of this matrix. Now we have to multiply them, because A theta into A. Therefore, let me write A theta multiplied by A. Let me write these matrices. This is the A theta matrix here. This is 1 minus iota upon 2. This is 1 minus iota upon 2. And this is minus 1 minus iota upon 2. This is 1 plus iota upon 2. This is A theta matrix. Now A into A is here, this is 1 plus iota upon 2. Let me now rub this. So we are just